of stuff.
We're now going to move into transformers.
Something right there, it's not really back here.
And we're not talking about monsters stomping all over Chicago.
Monsters?
Come on, you guys. Humor. Transformer. Isn't that what they call them?
Yeah.
Transformer. Yeah.
Oh, Michael Bay movie?
I have no idea the name of any actors. Last actor I can remember is Sean Connery. That's how old I am.
Oh, Lord. That's pretty good. Let's go that.
Okay. All right, so as we dive into transformers and filtration, in this realm, we're pretty universally talking about AC only. There are going to be some instances of pulsed DC where we use a transformer. Probably a really classic common one is in the form of pulsed DC to provide secondary ignition and spark ignition to spark ignited engines. Okay, that is a transformer. And it is, in this case, used in the DC world, but it's pulsed DC to create a varying or a somewhat constantly changing magnetic field. But for the most part, transformers are an AC device, and in fact, the big advantage of AC is the fact that transformers allow you to transform voltage and current with each other. So that the net exchange of power remains the same, but you can raise the current and lower the voltage, or raise the voltage and lower the current. That's hugely advantageous to us. And if we do it right, we can do it with a pretty significant degree of efficiency. Okay, these do get a little bit warm, so you do lose a little bit, but for the most part, they're, 98, 99% efficient. Assuming we can address the inductive and capacitive reactance problems. Okay. All right, so a transformer is essentially two or more inductors in close, and I'm going to use the word magnetic proximity. They themselves don't necessarily have to be touching each other or wrapped around each other. I can use a magnetic conductor, a permeable conductor, like is drawn here, an iron plate where any magnetic field that forms is going to form and stay inside the magnetic plate. So as I start inducing a magnetic field in here, it's not going to form out in the air like this. This drawing is a little bit wrong. What it's going to do is it's going to jump into here and then jump back out as the magnetic field collapses. Jump back in, jump back out. Now, there's a point where I make this so long, it makes it very inefficient. So I'm going to want these two coils, to some degree, to be fairly close to each other, just because why make it bigger than it needs to be? Why make it heavier? But presuming a whole bunch of factors, and you can see all the factors shown there, phase relationship, as well as permeability of the material, magnetic permeability of the material, resistance and inductive reactance of the conductors, nature of the load, etc. The efficiency of this thing will vary. Ultimately, the goal of this will always be to maintain about the same amount of power coming out that goes in, but a shift in current and voltage. There's one exception to that. There are times where we will use this thing not so much for the sake of shifting voltage up or down, but because this is a little bit dirty. Instead of being a nice clean sine wave, it's got some noise in it. It's a little bit imperfect. The magnetic field can't move fast enough to make all of those little imperfections translate into the magnetic field. So what will happen is this will put the same amount of voltage and current out in the same form, but it'll be a lot cleaner. So in that case, we're using it just to filter. Okay. The other thing is, because power is the result of the sum of amps times voltage, if one goes up, the other must go down. Okay. Now there's some. There's also another thing that's going to occur is, remember when I showed you we were talking about inductive reactance? It creates a phase shift. So with Eli the Iceman, voltage and current lag. So the current lags behind the voltage. Well, I'm going to get current lag here and then additional current lag here. So in truth, the output of this will be phase shifted 180 degrees out of this with respect to the current. So another reason to use this may be if I'm intentionally trying to phase shift one of the phases, I could use a transformer just for the sake of doing that, you know, if that's a goal that I'm trying to accomplish. Okay. So again, you will lose a little, but they're usually pretty, 99% efficient. They're pretty good. No moving parts. About the only thing that damages these things is too much current. I think the other thing that probably can occur, copper in and of itself, if it's well protected from oxygen, doesn't change too much over time, over many, many years. The insulation, on the other hand, could break down because that's usually made out of some organic compound that, over months isn't a problem, over a few years isn't a problem, but over 150 years, for some really long period of time, the insulation does eventually start to break down. So we can draw them diagrammatically a bunch of different ways, but typically we just use the little half circles, the little half loops, to depict a coil. So, and you can see there's a couple of versions. There's a fairly small one. And note here that we've got a lot of turns with a fairly narrow wire and a few turns with a fairly thick wire. So one of the things we're going to do, just for saving weight and size and as well, sort of increasing resistance, if we want let's say that the input is on the left, if we want the input to be fairly high load and high voltage, we're going to make the wire a little bit thinner so that it provides some additional resistance. We're going to give it the higher voltage, and it'll produce a fair amount of magnetism, which as that sine wave goes into here, the magnetic field is going to go boom, 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 back and forth into here. And each time it cuts across, or it's built up in here, it's going to cut across here and cut back out. The magnetic field will cut across a much bigger wire, which has fewer turns, but much less resistance. Okay, so a lot more current can flow through it. So the output, the voltage will be dropped, current will come out. Now another one that's being designed, these two guys building up this big transformer here, that puppy's a serious transformer. Okay, that's a big spindle that once they've done wrapping it, and a bunch of plates that secure it all together, the inner core comes out and they have this big huge transformer that they can then put whatever core they want in. It's entirely likely, given the multiple wires that are going in, that the different windings are all wired together. They're all wrapped around, they're all wired in the same bundle. That's perfectly acceptable. Okay? As the magnetic field is induced around one, it's going around the other. We do this very, very commonly with ignition coils. Okay? So that's a big transformer.
What's the ratio? The turn ratio.
What do you want it to be?
So it could be 1 to 10 or whatever.
Whatever you want.
So for every.
So in the case of, let's use a magneto coil. So in a magneto coil, if I look at the little generator in there spinning around 200 or 300 RPM, It's probably top end is producing maybe 20, 22, 24 volts, something like that. And I want 20,000 volts out of it.
Right.
Okay, so the ratio of turns is going to be whatever we said. Let's say it's 20 volts to 20,000 volts. So the ratio there is going to be 1 to 1,000, right? It just depends on what you've got going in and what you've got coming out. And the ratio there is going to be fairly linear. I could make both wires equally thick, but that would make it unnecessarily bulky and heavy. Think about, if I've got, let's say I've got 100 turns there, and at a ratio of 1 to 1,000, that means I've got to have 100,000 turns on the other side. 100,000 turns at that same wire diameter, that's going to be one huge coil, right?
Mm-hmm.
Now, of course, the other part of this that I think is kind of magic is their ability to take, particularly in high voltage coils, take and make a wire that thin. Not only make it that thin, but then insulate it really well. And the insulation is really thin. And then wrap it all the way around that thing, as many times as they wrap it around that thing. Now, you and I both know that if I did that, I'd get just about to the end and the other end would snap off. Okay? And these guys, they mass produce that thing that costs $1.98. To me, that's the part that I just, again, it comes back to this manufacturing, how they do that. So, again, a couple of ways of doing this. Note I've got 2 coils, magnetic field jumps back and forth, reverses, keeps reversing. I've done that. Or I take a permeable core like this, and I have a primary and secondary, and I don't know which is which. And now the magnetic fields are going to build up, and snap in and out, snap in and out, snap in and out around both sides of that. And in fact, in particular, in this particular one, you'll note that's got an inner and an outer and an in and an outer. Here I've got an inner and 3 different outers. It's actually very, very common to do this with transformers. And it defaults back to the idea that with resistors, we had preferred values. With capacitors, we had preferred values. Well, with transformers, we do the same thing because we have a bunch of preferred voltages, right? Don't we typically, everything we plug into the wall, we expect it to be 115 or 110 volts, whatever that value is? So I'm going to make a whole bunch of transformers as a manufacturer of transformers that all have those 2 leads there that are intended to accept 120 volts at various different power values. And then on the output side, I'm going to say, well, what are the most common users? Well, people like 12 volts a lot. Some people like 36 volts or 24 volts. Okay, because of batteries, we sort of have those preferred values. Now with computers, people like 5 volts. People like, so what do people want? Well, the transformer manufacturer is going to pick the ones that are the most common. So they might have, 12 volts here, 24 volts there, or 5 volts, or some combination. Or they may have a whole bunch of different taps. And in truth, it's very common to find transformers installed with only a few of the leads being used. So there's a variety of different transformers. Some of them looks like air gaps. These one are just very, very few, very little inductive relationship happening there. This one here, it looks like you can tune it by moving the permeable conductor or the permeable magnet inside up and down, and wherever that piece of metal, that slug sits relative to the 2 coils will vary how much inductance or how much magnetism is induced across it. Same thing here and same thing there. Little bitty adjustable transformers. Okay, so we often use the term step-up transformer or step-down transformer. What we're referring to is what happens to the voltage from the input to the output. So if I say it's a step-up transformer, I'm saying that the voltage comes in at one value and comes out of the secondary at the higher value, at a higher value. So primary is always the input, secondary is the output. The transformer doesn't care which way it's hooked up. Okay, functionally it doesn't care. The amount of resistance in the wire may matter, but functionally, the transformer doesn't care. So if I say it's going to be a step up, that means I'm expecting the primary to be at a voltage that's lower than the secondary. The presumption is I know the current is going to do the exact opposite, right? Okay. I may also design it to include an internally installed rectifier. So I may make a nice little power supply unit that not only steps up or steps down, but then converts it to DC. So on the output end of this thing, I get one end's designed to plug into the wall, the other end's designed to put out 12 volts DC. Okay. And in fact, I could package it all up, put some filters and do a bunch of other things, and sell it to you when I sell you your laptop. Right? Okay, put it in a little hockey puck there and put a nice little wire coming in, a nice little wire coming out, label on the bottom. Okay. It's, again, as I said earlier, common to make for these things to be built in sort of a multi-use manner, so that I, the manufacturer, I can have 100 different products that meet the goals of 10,000 different folks interested in buying my products. Okay. So some other interesting things you can do, and the A is pretty logical. You have input, magnetic field, and does this to the output. It looks like it's got a little bit more turns, so it's going to voltage step up. Here, we're going to, this is a little strange, but it actually does step the voltage up. Okay? That is one way of wiring it. It's fairly uncommon. Then, you know, there's several different diagrammatic ways of doing it.
That one, B will step up more voltage than A.
It creates, for lack of a better description, it produces a much tighter magnetic coupling, so less energy loss. However, the downside is it doesn't filter. The electrons that are going in come out. Whereas in A, it filters. Okay? The C is kind of the same as A. It's just using a permeable separated coil. And then what are they doing with D? Because they took the two coils, the magnetic fields are going to be operating at the wrong direction, aren't they? So you're going to get zero coupling between the two. So the magnetic fields expanding in and out, going in and out, aren't cutting at the correct angle. Okay.
So what are they transforming?
I think they're just showing you that drawing it that way. I have no idea what that circuit would ever be used for.
So the permeable core, is that just for extra efficiency for the transformer, or?
Oh, absolutely. Because now permeable core means all the magnetic lines of flux are going to go into there. As they form, they're going to build up and they're going to stay right in there. If I don't have a permeable core, they're going to be out in the air, and then they're going to come back down, and they're going to be out in the air, they're going to come back down. And so the efficiency or the effectiveness of this can change if I move a permeable core in and out of there. So I can cause this thing to be quite a bit inefficient if I wanted to. Let's say I was trying to create a little bit of amplitude loss in a circuit. Okay, but I didn't know exactly what that needed to be, so I needed to fine tune it. So let's say I was trying to drop a certain frequency out of a carrier signal. So I could use an adjustable transformer like this, move the core in and out to tune that to a specific frequency for which the transformer grounds that particular frequency. All other frequencies continue on through, but that one either grounds it or passes it on to a different part of the circuit. Maybe that's the desirous thing. You know, it's like the tone on a audio transceiver or a Markov beacon transceiver or something.
So that's what you were talking about when using a transformer for a filter.
Right. Well, that's one kind of filtration, yes.
Okay.
Another filtration is when you're just trying to smooth out the input.
And that's a natural occurrence of
Yeah, the advantage of this or that is little bitty fast speed spikes won't make it through the filter.
Right.
That's particularly true if I take and put a capacitor here to ground to allow the high speed spikes to actually ground out. So I'm going to ground them out, create an inductive load here, so it's easier for the spikes to go this way, and a much smoother signal gets picked up here, and what comes out of here is much smoother, and no electrons in this side actually ever get to here.
Thank you.
So when they get big, so like these things right here, that sort of looks like the big green box that's right outside of David's window that supplies all the power into the building. And in truth, this sort of doesn't show it that well. Usually these not only have big banks of or transformer in there, but they also have big banks of capacitors inside as well to try and reduce inductive reactance. So in this particular case, it's fairly simplistic. They're showing primary coil, secondary terminals. Again, they usually have multiple ins and outs. They then will have either a pump running it, or more often what they do is they design these radiator elements to where as the heat builds up, the oil just starts rising. And as it starts rising, it flows out this way and cools down. Well, as this cools down, it starts sinking. So these just naturally circulate once they start warming up a little bit. Okay. Now, oftentimes they'll either put that behind a fence so you can't get to it, or they'll put it in the big green box, or somewhere or another to keep. So these things can actually get pretty hot. The other thing, for many years, I don't know that they do it as much anymore, but the oils that they used in there were pretty toxic stuff. You guys might have heard the term PCBs. Okay, yeah, pretty nasty stuff. However, in the big magnetic fields, you know, a lot of materials will begin to degrade pretty quickly. So they have to come up with something that can stay in there for many, many, many years. And so the best core is going to be iron. Air is going to be not so great. There are other materials they can put in there that are even less permeable. How about stainless steel? Okay, stainless steel, just a little bit of nickel added to iron, and it actually shields the magnetic field. So there's a variety of things they can do to interfere with the amount of inductive coupling that occurs between the two, the secondary and primary. All right. So again, the schematic symbols, air core, some plates like that is iron core. The reason we draw a couple of lines is we're actually trying to exemplify that any iron core that sits in there is going to be laminated. We want to laminate it because as the magnetic fields build up and collapse around iron, the magnetic fields are going to try and go into the iron, and as they go into the iron, they're also going to try and induce current going circularly around the bar of iron. Well, if I make it in a bunch of thin plates oriented to the axis that it can go, those currents can only go in a very thin plate this way. So they're going to consume a little bit of energy. Those eddy currents are going to happen, but I've made them, I've interfered with them as much as I possibly can while still leaving this component permeable. Okay? So there's a tendency for the magnetic lines of flux to jump in cleanly And they may do a little bit of circular this way, but you'll get no circular action that way, which would cause us to lose a lot of energy in the form of heat, right? Also cause these things to run pretty hot. So like I said in that, showed in the earlier slide, you can either fully isolate one part of the circuit from another. You could do it on that example B where you get much closer coupling. Your phase relationship doesn't shift any, but you still get the advantage of the jump up or jump down. It doesn't filter any at all. And so ultimately, they will affect the impedance of, I've already said that one, they'll affect the impedance of the AC circuit. So if that matters, you'll have to accommodate for it. In some instances, yeah, we're trying to be efficient. It's sort of something that gets used all the time, like this building. Lights are on all the time. The tennis court lights are on a long time. Other stuff's on a lot. Let's see if we can make it a little bit more efficient. So we're going to try and accommodate for that. Other users, like an airplane, might well be that the weight that it takes to accommodate for that isn't worth it. Versus a few extra gallons of fuel for every 24 hours of flight time. Okay. The other interesting thing is you could also tap off in a couple of different ways. Given that you've got either a neutral and a hot lead, or two hots if you're in the two sides of the phase, or I can even do it with three phases. I can run a parallel load off of the lines, like on the left, or I can run it in series off of one of the lines. Now, most often we do what's on the left side. So what will come to the plug socket will be, these two wires will come out and your plug socket's right there, and you're plugging into that. And somewhere these two lines run into the main bus in here, and they run into it in that parallel manner. But if you look off of there, each one of those are paralleling off of the two lines. It's very rare that we do the Christmas light thing there. There are instances, if you really, really want fine sensitive reading, like in the form of a meter, then you would break in like that, and that would give you that there might give you current reading. Okay. But for the most part, we don't wire them this way. We do it that way. So, and then this sort of gets you the idea. So A looks like we're stepping down, and it's a ratio of 10 to 2 or 5 to 1. So if I put 10 volts in, I'd get 2 volts out. And at 2 amps in, I get 10 amps out, right? Okay, so that when I do the math, the power is going to be pretty close to the same. Again, there's a K factor, a little bit of loss due to the coupling weak variances. And then the bottom one is going to be stepping, up, right? No, I'm saying that wrong. Yeah, so that one's going to be stepping up. Upper one's going to be stepping down.
So you're saying 10 volts?
So this would be like your ignition coil. So I'm going to put in 12 volts here and get 100,000 volts out. This is going to be going the other direction. It's going to be stepping it down. So this might be 120 volts in here, and I'm getting 12 volts out for your computer. Okay. Go Benadryl. Yeah, make your head hurt. Whee! So this one sort of quickly shows you how to do the math. So if I came up, and we're going to assume the ratio is 10 to 100. I can then say 10 volts or 10 amps at 10 volts. Out here I'm going to end up with 1 amp at 100 volts. and then my load of 100 ohms here, and the AC load here. So the power here, if I do the power on this, 10 times 10 is 100, right? Okay, 1 times 10 is 100. The voltage drop across there is going to add 100 ohms, is going to be, okay, 100 volts. That's all logical. That would all follow Coulomb's law, Coulomb's ratios, so and Ohm's law, either way. And since I didn't rectify, the load obviously can't be a DC sensitive load. Okay. So then this one just shows a variety of different ways of connecting them. So in this particular case, we have, it looks like a parallel and a parallel transformer, 2 parallel transformers on the input side. On the output side, we put them in series. So now I've got full voltage, half voltage, and half voltage, right? Here, I've only got 1 voltage coming out, but twice as much current. So, and again, this is showing them as independent transformers, but in truth, I could have multi-wrapped all of that into one big bundle with just multiple taps coming out. And the taps oftentimes will be color-coded. So it's very, very common for these little AC biscuits. 2 black wires go in. Either one's neutral, one's hot. Doesn't really matter on those. On the output, you'll have a yellow, a green, a blue, or something, but you have to find the part number on there, go pull out a spec sheet on it, and figure out what all those values mean. Okay. Yeah, so here's some fancy little multi-tap ones. So there's an example of, looks like I've got a neutral, so this actually gives me some definition. Neutral, hot, and then earth comes to here. What earth is going to do is it's going to make sure this chassis gets grounded to earth. So in case a short does occur, instead of coming back through you, the user, it's going to go out to here, through the chassis, into that wire, down to the planet, all the way back to the nuclear reactor. Okay, through the planet, or through Earth. So this might be a diagram of such a device. Black and black, only in this case it looks like we went white. There'd be a green coming off of here somewhere. And then multiple different taps. So 120 in, maybe we're getting 120 and 240, or that doesn't look even, so maybe we're getting 100 there and 200 there, or something like that. And then down here, it looks like we're getting 5 volts. It says 5 volt windings, but this could be 5 volt positive and 5 volt negative, maybe. Okay, same thing could be happening there. We'd be doing all kinds of cool stuff. This one over here, it looks like they did, this is actually, looks like a 3-phase coil, so a transformer. So all 3 phases are coming in, and then there's multiple taps of all 3 phases coming back out. Which I think is one of the next slides. Yeah, now here's another one that's, again, a pretty prepackaged device designed to have 100 volts or 120 volts going in at 60 cycles per second. Then it's putting out 360 volts. So this might actually be for the older style fluorescent lights. It's going to use 360 volts to drive the electrodes out on the end, and then it'll use a fairly high current 6.3 volt to drive the starter to get the ion field excited enough to start emitting light. So again, very, very common. What do we call them when we put them in lights up here? We don't call them a transformer, we call them a ballast. Yeah, because we don't want our ship to sink. I mean, wait a minute, let's flip upside down. Ballast, where the heck did that word come from? Well, we call it a ballast.
Because they're
But
heavy.
what it really is a transformer with a couple of big capacitors in there. So, and again, then this, and I'm not going to throw this kind of math at you, but this essentially shows a multi-tap transformer schematically drawn as two individual output secondaries, right? But they could actually be connected to each other. That middle lead could be the same wire. That's what's sort of strange about these things. Literally, from the perspective of this device, that's a load. From the perspective of these devices, this is a power source. If I disconnect one of these devices, the resistance goes to infinite here. The effect of the magnitude of this device on this device goes to infinite. And so this guy here, its impact on the circuit goes way up. Its resistance or impedance to the circuit goes way up. So the amount of current will drop down. And that's why you can, leave your hockey puck plugged in, and when you turn the device off, it's just sitting there idling. Yeah, the voltage is flipping back and forth, but the current really isn't happening because even though it's still connected, because this now just starts producing a counter field that superloads this and causes the resistance to be very high in there. Now that said, it does stay a little bit warm. If you're not going to be using your TV for a while or any other electronic device that probably has a transformer in it for a week or month or whatever, unplug it. Okay. Otherwise, you're wasting a little bit of power, a little electricity. Now, more sophisticated digital components, what they do is they automatically, they'll use a transistor of some kind to completely load shed it. When it's off, they shut it down to where all it's doing is using a few milliamps to monitor whether things have been turned on or off. And if they're in the off state, they load shed completely, and the circuit sees this as one of those wires disconnected. So yeah, here we're starting to get into the multi-tap, where essentially all of this is bundled together. So all the magnetism by this is felt across everything. That's where it gets a little confusing. But, so theoretically it seems a little confusing, but manufacturing wise it's really easy to make. I just take and make one big coil, and somewhere in the middle I can, have another lead coming out, right? Same thing, that would be stepping down there, right? Makes it much, much easier to build these things. And in fact, I can have a bunch of different taps, some of which don't get used. So again, as I said, because we're going to use an inductor, and it's purely an inductor in most of these instances, current is going to lag 90 degrees out of phase behind voltage. So they hit the voltage will be instantly, 120 volts. Current will start building up as the magnetic field builds and expands. It'll reach maximum about the time the voltage is dropped down to zero at 90 degrees in the sine wave being drawn. That magnetic field is going to be inducing voltage and current in the second coil. In the second coil, the current's also going to lag 90 degrees. So the summation of the two phases of lag is going to cause the current in to be exactly 180 degrees out of each other. That's no big deal. Okay, so I go out here and I got this transformer, let's see, T4 over there and T5 there, T2 there, and they're all kicking things up to 480 volts. Those are all taking everything 277 to 480. And they're doing it in 3-phase. However, one of the devices that I've got over here, that transformer has kicked it up to 240, or kicked it up to, let's say it's kicked it up to, let's say 277 up to 480, but then another out there on the end, I've kicked it back down to 277. And I'm coming back into the rest of the circuit. The other two leads of 277, right? Now I've got two leads of 277 that are exactly 60 degrees out of phase with each other like they belong, but, or excuse me, 120 degrees, but the third one has been shifted because of the extra transformer in there. It's been shifted 180 degrees out, okay? Which means ultimately it's 60 degrees off of where it's supposed to be. So I'd end up having 120, 120, 60, and then a big gap of 180 till the next phase comes back on again. Well, that would cause whatever I'm running to not be equally balanced. The three different leads running to each other wouldn't be equally balanced. So if I then drove that back into the compressor, you'd hear the motor humming really weird, doing funny things. So whenever you design any circuit like that, you've got to make sure, if you're doing multiple stages of transforming, that you keep things within phase of each other. Most of the time within a building or within a device, it's not too big of a problem. Where it becomes a problem is when, like for the college, you have an entire ring of 3-phase power going all the way around. And then I jump power from here over to the tennis lights, but then I have a backup power source coming to the tennis court lights from another place that's out of phase with what's happening here. Well, if I end up having both of them interconnected, now I'm going to cause a problem, right? I might have lights that actually randomly flicker on and off, do all kinds of weird things. It's really, you don't see this to be a problem until you get into more complicated systems. Theoretically, the engineers have fixed that before you get there. So a big commercial building, a large tall commercial building, particularly where they're using, say, 2 phases for floor 1, 2 other phases for floor 2, and then the other 2 for floor 3, but floor 4 and 5 need all 3 phases, and then as you go up the building, you start getting phase shift problems. So this just shows the shift. In this case, current being lagged 90 degrees, and then voltage being lagged another 90 degrees out of phase, such that the two different currents, in this case the two voltages, are now staggered exactly 180 degrees out of phase with each other. And if I reverse that, the current would be out of phase, either one. Okay, does that make sense?
How do they sync the phase? Like if you have a solar, right, and you're trying to sync up, or a generator system, you're trying to sync up
to AC?
Yeah.
Well, first thing you're going to have to do is make you're going to have to, because the solar is going to come out at you at DC.
Right.
So you're going to have to put it through an inverter, and then the inverter is going to have to sync itself to existing AC systems. Okay, so one of the things it's going to have to do is monitor AC, or it may load shed. Okay, so in other words, when solar is running, it runs strictly on the solar, but as solar starts to decline, it then flips over to. And you may also have a battery bank in there that solar is charging, that during the period that the batteries are charged up, they also run. Oftentimes it's easier just to flip from one to the other, and they can do it in a controlled enough manner that you don't see the lights flicker or things turn off. There may be a very brief period there where the phasing is a little bit off, but it's not enough to hurt anything. It's happening pretty quick. But again, you're going to have some pretty sophisticated circuits monitoring to do that. Same thing is true with all the wind generators. You know, all the wind generators out there, God goes, and and blows real hard all of a sudden, right? Well, they better change the pitch on those blades really, really fast and do some stuff to keep up, keep the RPM pretty constant coming out of there. Now, it may well be that after, a couple of 300 days of running this thing, they figured out when the time period, okay, right about 4 o'clock in the afternoon, the wind starts getting really wonky around here. So we're going to be ready for it. We're just going to come offline from these generators. We're just going to disconnect them, let them free spin a little bit, put the brake on, do something like that, because we know during this window of opportunity, it's a little too hard to control. Okay, they learn that from experience, but so yeah, as I was saying earlier, these guys when they're idling, they don't use a whole lot of power. They do get a little bit warm. And I'm going to run just a little bit over and we can finish this section. I got about 10 more slides. So in idle, they're gonna generate a little bit of heat. Okay. New world technology, the kinds that typically use a digital circuit. The transformer comes in, rectifies to DC, and then all conversion is done there. You'll find those are much lighter, and they don't weigh all that much. They have very little copper in them compared to a standard transformer. But even a standard transformer now, they usually control it with an input transistor that shuts it down if the output isn't being loaded. So in other words, you unplug the computer, it says, well, I don't have much output, so let's turn off the input side of the transformer. And it doesn't really turn it off, but it brings the impedance up to, 100 mega ohms. Something to where the amount of current is just a very small amount. Okay. But again, they do tend to work pretty well. So we can also make these guys 3-phase. Well, I just take, now remember, so coil A, B, and C, run it that way, and then your output, run it the other way. Okay, so we can triple wrap these, or again, there's several different ways of doing this. Magnetic lines of flux, one's heavier, but it has slightly better coupling, the 5-leg core. So each one of these sets of windings would be, and they typically use, for transformers with 3-phase, they'll, and I can't tell you which is which, but they'll have capital ABC for one side, primary, lowercase ABC for secondary coming out. Sometimes they use alpha and then numeric. But this then shows essentially the same thing, but sort of drawn as they're coupled, still delta wound versus looking like the delta configuration, right? And they both accomplish the same thing. So this side, if this was the input, that would be giving the output to here. Now the upside of this is all of these are going to be phase shifted. So all of these are going to be phase shifted, but they're going to be phase shifted the same amount. So as long as I don't intermix these two somewhere down the road, which you normally wouldn't because of different voltages and different currents, the relationship between A, B, and C remains the same. Then this just shows the more common Y version, how they're actually coupled versus the diagrammatic way, and then neutral just goes to your white lead. So all these little gray boxes around that say T1, T2, T3, T4, that's what you're seeing, and that's what's inside there. Oh, there's a whole bunch more wires. Same thing with the little Hobart cart that is used to power the turbine, the Pratt & Whitney. Same thing. Okay, big 3-phase transformer. So I don't know, can you see it here? Yeah, you can sort of see it. See all the little laminations? A little harder to see there. Not only is laminating, and by the way, they put just a very thin layer of shellac on there. Actually, a little bit of current will conduct through there, but the fact that they're physically separated, the current doesn't like to jump across. It's very resistant to the magnetic lines of flux to do that. So they just tend to circularly travel in there. They tend to stay within each plate. But the other big advantage of that laminated core is to make a core with those kind of funny shapes out of a solid piece of metal would take a lot of engineering versus stamping a bunch of sheet metal and then stacking them all together. It makes it a whole lot easier to make. So just the lamination from the perspective of manufacturing is a lot easier to make. It does a really good job of reducing eddy currents and therefore the amount of heat that gets built up inside the iron plates or the iron core. So and then I've already said you can make it adjustable by moving the core in and out. You can also do the same thing with capacitors, by the way. I think I showed you guys earlier. So yeah, this then shows, here's one where the core slug sits in here and then you can thread it up and down. This one, you can actually pull it all the way out and dial it in. The more you move it in, the more you move it out. That changes where the magnetic lines of flux either floating in and out of the air or concentrating in and around the iron core. Okay, so what this does is it makes it variable in terms of the amount of inductive coupling. Okay, so in this particular case, you'll see they say A or B. They'll say 1 to 3 millihenries. So remember, we were looking at trying to define or trying to calculate inductive reactance. We used henries. Well, depending on where you adjust it, that's what you would get. B, in this particular case, depending on the rest of the circuit, you would move that core in and out to try and tune the circuit specific to, in this case, it looks like 40 megahertz. Okay, so I might be using that to filter out or bypass or cause 40 megahertz, whatever's happening at 40 megahertz, to be shifted out of the rest of the other bandwidths that are happening on that wire. So for example, let's say I had a signal that's completely stealth and can't see anything. Let's say I had a signal that's doing this. Something like that. This is at 40 megahertz. Okay, but the signal here is the audio tone that I'm looking for. So I'm transmitting amplitude modulation on 40 megahertz, and I want to separate the audio tone from the 40 megahertz of oscillation. So I would filter this through a bypass inductor to ground and filter this through a capacitor out to an amplifier that would then amplify that audio signal. And whatever that audio signal, maybe that's the tone from a marker beacon. So if it was like 75 megahertz, that would be the tone. And then there might be one of what are there, 3 different tones? The outer marker, inner marker, and there's one other, I'm missing one. Yeah, far pilots, I'm missing one, outer marker, middle marker, there, the outer marker, middle marker, and, actually inner marker or misapproach marker. Okay, so depending on what I'm trying to do there, I could be using this thing, again, to filter or tune. So filtration is always about trying to eliminate unwanted aspects of electricity or separate the desired from the undesired. Now, maybe that both sides are desired, but in most cases, you're really trying to eliminate one part. So one thing I could do is, let's say I've got an AC wave on a DC voltage. What does that look like? So I could have a line where this is 0 volts, and I could have an AC wave on it, right? But if I put 10 volts of DC in there, what I'd end up with is this. Okay? So maybe I need to do something to filter that down. Well, one way to do that might be a transformer. Okay, so I could run that through a transformer, and the transformer is only going to respond to the AC-ness of it, right? It's not going to respond, so what's really going to be happening is the electrons are going to be going this way for a while, and coming back to here, and this way for a little while, and then coming back to here, and then this way for a little while, and coming back to here. So note that they are moving progressively a little bit. Well, once that magnetic field is pulsing back and forth, it's just going to pulse back and forth due to the AC nature. So the secondary will never see this DC portion up here. So what comes out of the output is going to be just the straight AC. Okay, so that's another example of filtration. I can also use a transformer or a straight inductor just to create impedance, okay, in a DC circuit. So I've got a DC circuit where the line's doing this, but it's actually sort of doing a little bit of this, okay? And what I want is just that straight like this. Well, this pulsing right there, if I send that through an inductor, it's going to suppress it. And in fact, if I send it through, if I do this, if I send that signal into an inductor here, come out, but then right there, put a capacitor like this to ground, the AC portion, or that radical portion, it's going to want to go through here. Okay? This is going to be resistance to that part of it, but it's not going to interfere with the DC portion at all. So it's going to clean the circuit up quite a bit. In fact, I could do it a couple of ways. I could double pass filter it. Do that on both sides. So anything that's left over here, it also gets shunted to ground. Okay? The DC portion can't go across because those are just open for DC, right? Okay? Very common to see this kind of thing. In fact, you buy those little Radio Shack. Well, there is no more Radio Shack, but you buy one of those little Radio Shack alternator noise biscuits. They've got 3 wires, 1, 2, and 3. Okay, that's all they've done, and they've tuned the inductor and capacitor to take out frequencies that are common to alternators. So yeah, so there is an example of the complex waveform, what I just drew, where it's got both the DC component, the AC component, and shifted up, it's got the DC component, both overlaid there. I can then use the filter to separate the two out. And it may well, I want to get rid of the DC, just to have the AC, or I may want to get rid of the other. It depends on what you're trying to do. So, for example, if you remember when we talked about our alternator, you don't get to see any of this. You're just going to see some of this. However, the rest of this can make a little bit of noise. So we can design a filter that will get the bulk of that and send it. In this case, the most simplest form is just a straight capacitor. If that doesn't cut it, then sometimes you'll need to put an inductor to create an impedance to this, the AC-ness of this. That then inspires it, more of it, to want to go across the capacitor. Okay, so again, and then of course, you know, there's a whole bunch of engineering math behind figuring out how to tune what that is. However, fortunately, most folks have figured it out. Now, what frequency did they tune it to? Well, the truth is there's some frequency where it's perfect. My guess is what I would do is I'd say, well, the average airplane engine flies along at 2,200 RPM or 2,400 RPM, whatever that value is. The alternator is spinning 6 times that, so whatever that frequency is, okay, times the number of phases in the winding, come up with whatever that frequency value is, tune to that, but make it as broad a pass filter as possible so that it filters all the way down and all the way up to a range reasonably well. But down at idle or maybe up above the top high RPM, it doesn't work quite as good. Okay, so and I've already talked about that. So a coil doesn't even have to be a transformer, although in essence it is acting like a transformer. If we're using it just as a coil for the sake of impeding flow, like what I've got drawn up here, we call the coil a choke. Okay, it's not truly a resistor, but it is imposing interference with the AC-ness of that part of the circuit. So we call it a choke. And choke, that sort of makes sense. Okay. And then we do the capacitive connection to take whatever is undesirous and choked and send that off the ground. I already talked about all this. I think I'm about done. Yeah, so this shows an example of what I've drawn. Your inductor, and then your output choke sends it to ground. You could also put it on the input side. Here it's showing both of these on the output side. This one shows we're going to bypass lower frequency stuff to here and higher frequency stuff there. Okay. So what this does is it allows for a little bit of this happening. Okay. And that completely absorbs. So what's felt out here is just nice, smooth electricity. Yeah, okay, so I didn't realize, remember I put this in here. So this is an example of modulating. So the carrier wave, in this particular case, I'll generate in the transmitter, well, what do we have, 40 megahertz? I'll have a metronome in there going beep, 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 making 40 megahertz carrier signal, okay, AC carrier signal. I'll then have Jimi Hendrix or Cyndi Lauper or somebody, I don't know, name somebody who's a musician, singing into the microphone, okay? I will then, in this case, amplitude modulate the carrier wave such that that's Cyndi singing away and the inverse of it here on, and so the pulse coming out from the antenna, the rarefication and compression occurs very symmetrically, but the amplitude of it is what's changing. The antenna that receives it gets that same signal, And then the amplitude filter is going to take and separate these two, get rid of this portion, and then send that part, it'll be a pretty weak signal by this time, into an amplifier, and then use that to drive the output speaker. Okay. The other way of doing it is, instead of amplitude modulation, what I could do is I could say I'm going to pick a narrow range of frequencies. Okay, so we'll say 108 megahertz. Really, I'm going to go 107.9 to all the way up to 108.1, or maybe even some smaller variance there. So then what I'm going to do is I'm going to have a signal that's even amplitude, okay, but I'm modulating the frequency within that range. So that's going to be a high tone, that's going to be a low tone. Okay, so that's frequency modulation, or FM. Okay, it turns out doing this, you can get much better definition, particularly over longer range transmission. Whereas amplitude modulation, a lot of things interfere with it in terms of the quality. It transmits a lot stronger over greater distances with lower wattage, but the quality is not that great. It is one of the reasons, part of the reason aviation still use amplitude modulation radios for all voice communication. Okay, some other areas they've gone to other technologies, but all of our audio comm is still amplitude modulation, because they don't care what my voice sounds like. They just want it to be relatively clear and be able to transmit 50 miles with only 5 or 6 watts. Well, amplitude modulation does that reasonably well. However, if you really want to hear just that nuanced high C coming from dear Cindy, FM or frequency modulation will do a better job of it. Okay, and in truth, because FM tends to not transmit as far, that means my radio station isn't going to have as much range, so I can reuse that same frequency a little bit closer. Okay. All right, so then we can get into the notion of passive filtration versus active filtration. So in passive filtration, we're really saying it's something like this. We design it around a certain noise and get rid of it. Active filtration, we're going to say, we're going to design the circuit and maybe even use some computer technology to listen to all the surrounding sound. Say the surrounding sound is undesirous. Okay, from the engine running and all these other noises, from the wind blowing. Those are all bad things. So we're going to listen to that. And we're going to listen to the audio that we know they want to hear. And then we're going to go inside the ear cups and we're going to actively suppress. We're going to create a counter sound that's the exact opposite of the undesirous sounds to cancel them out. Now that's the guys early on we called it Dolby noise reduction. Okay, that's active filtering. And now most of your fancy car electronics, audio electronics, as well as in-house Bose radio, all this fancy stuff, that's very, very active filtration, where it's listening to to all the sounds around you and saying, what can we do to cancel those undesirous sounds that will interfere with the audio signal you're trying to listen to. Now, of course, if you have to do that to a whole room, that's a fair amount of energy, right? As opposed to the volume inside a couple of ear cups. Okay. In the case of a movie theater where they've done full Dolby noise reduction, they're actually doing it to the entire room volume inside a pretty high-powered speaker systems. What I will tell you is the active noise reduction in the form of a headset around your ear cups, it's remarkable. It's not only is it remarkable in terms of how much noise is reduced, but what's really remarkable is how much wear and tear the noise has on you. I mean, wearing a standard non-active reduction headset, after a couple hours, you're just like, okay, I'm done flying, man. With active noise reduction, 10 hours later, it's like, okay, I'm still pretty good. I mean, it's just amazing how much that intense vibration of noise wears and tears on you. Okay. So yeah, and then this is just showing what an isolation transformer, I already talked about that. That's an example of what it's doing to clean it up. Okay. This is what happens when the transformer is sad. You know, I don't know, maybe a bald eagle's flying through there and poof. Or some idiot decided, hey, copper, let's steal it. Okay, poof. What do you think the flame is coming from?
The transformer.
Huh?
The transformer oil.
Yeah, whatever the coolant is. Okay, the metal probably copper or steel housings. They're probably not going to burn like that. However, whatever that oil is, it's probably what's burning, and whatever it's got in it's probably pretty toxic. So whoever you are putting that fire out, you probably don't want to breathe that stuff. Okay, or be downwind of it. All right. Sorry, I ran a little bit long. Let's take a break.
I have a question.
Question, sure.
How are they with the wireless technology and cell phones now with big charging? How is that? I mean, like, what I'm confused about is because Tesla back then, they didn't have diodes back in the 1900s, and Tesla was able to do wireless things, and now they have diodes, which would help with the wireless technology.
Well, so Tesla, and it was really Marconi actually did the wireless, but they still had capacitors, they still had inductors, and that's primarily what they're using, as well as quartz frequency generators. And so they did all of this without digital technology. You don't need any of it. All you need is something that will start with a small electric signal, like a quartz signal generator, that you can then tune to a variety of different frequencies, amplify the heck out of it. Then that becomes your carrier frequency, and then modulate it. Now, it's important to note that when we originally did this, we did this in really long wave frequencies. So the difference from peak to peak, 100 meters between, and the antennas were hundreds of feet tall and really separated wide. And Marconi, in fact, one of them, I think the closest antenna to us is up in Drake's Bay, north of San Francisco. They've got a museum up there, etc. But he communicated all the way around the world. Long wave. Long wave radio, I've got a good friend of mine, in fact, he used to teach here. What was he telling me? He just talked to somebody in Iceland, and a couple of days before that, he talked to somebody in the South Pole from out here in Oklahoma. Okay, ricocheting long wave transmission all the way, from the ionosphere, and the waves are so big that they're literally going all the way across, up to the ionosphere and back down to the planet, propagating super, super long wave transmission. Okay, cell phone technology, instead of being 100 meters long, they're more in the range of 200 gigahertz, so they're way less than a millionth of an inch frequency band. So you can compress a whole bunch of data in that, but it doesn't have very good range. So you need to have a cell tower pretty close, like on top of the big building over there, that big water tank thing. Okay, there's one there, there's one over here, they're all over the place. Okay, however, there's so much data can be put on those things. As you're moving along, they're triangulating and figuring out where you are. And in fact, now all cell phones have GPSs, so it's telling the system where you are. And as I start getting farther away from you and closer to you, the data system just says, well, we can both hear you, but now we're moving you over to here. And then we're going to move you over to here. And then we're going to move you over to here. So in the old world days of cell technology where they didn't want you moving too fast because they couldn't tell where you were, that's been done and gone since about 1985. So the whole buzz around not having cell phones in airplanes or moving off road. The reason they didn't want them moving off road is because they put all the cell towers along the road, expecting where you would be. You get an airplane, you're not on the road anymore. So it confuses the cell towers where you are. It no longer matters. Since we went to full digital systems, which started in about 1985, and it was pretty well done by about 1996, that hasn't mattered. However, the FAA told you a big fat lie. And for good reason. The FAA, when the flight attendant stands up and says, I want y'all to shut up and listen to me, the FAA wants you to shut up and listen to it. So during those periods of flight, they want all the cell phones, they want everything turned off. So they just kept that law in place. They've had the FCC and several others work with them to keep those laws in place so that the flight attendants can control their audience when they need to control them. Because particularly during takeoff and landing, you got it. Something goes sour, you want everybody paying attention to the flight attendants, right? So the truth is, cell technology, the other advantage of the cell technology at really high frequency now is because they are so much closer, the amount of power that they're emitting is way less. So it means you're irradiating yourself quite a bit less. I actually have two different friends that were in the construction industry that died from brain cancer from the older cell phones. The older ones where they didn't have any towers and they were really, really strong. They actually, one of the guys actually had a big band of melanoma forming just right up the side of his head because he was on the phone all the time with his head next to that antenna. Which is where kind of the whole foil hat thing, people are like, oh my God, I don't want a cell tower anywhere near me. Yeah. Well, that's not so much so anymore. I will say I would much rather be closer to a cell tower than one of those. Okay, I don't want to live under the wires coming out of San Onofre or any other big power generating station. Okay, while they don't, you would say they don't have a lot of current relative to the voltage, they still have a whole bunch of current given that they're powering all of Riverside or, all of some big area. So to me, that's far more dangerous than that. And they go boom like that, start a fire, and everybody dies. It makes them sad. Aren't they saying now that was one of the primary causes of the Northern California fires? One of the PG&E wires failed, came down, something happened, and that started that's what the last thing I read was, I think it was, or at least one of them was started by PG&E maintenance.
Kind of like 21.
Mm-hmm.
They're like 21, 22 fires.
But, well, one of the big ones, at this point, it's like 8,400 structures gone. Was the one started by, the one that burned into Santa Rosa and all through there. Boy, if they really do prove it that PG&E screwed up, they've got to wonder what the bill for that is. Holy cow!
They'll just raise your bill.
Huh?
I said they'll just raise your bill.
Well, the issue is, was it an accident or something that was unpredictable, or were they negligent? If they were negligent, then no amount of raising your bill helps them. They go after stockholders, they go after CEOs, they go after everybody. So it kind of depends on how that played out. So, all right, well, let's take a break and then